Hello everyone, here is our work about applying exploration strategies of reinforcement learning into structured topology optimization. This is our outline. First, let me introduce the research background. Because the natural resources are limited, computation and the environmental problem is severe and severe. Structural optimization is more and more important. The types of structured optimization from higher level to lower level are first, topology optimization, changing the structural topology. Second, shape optimization, changing the structure shape, not generating new hosts. And third, size optimization, only changing several geometric parameters. Density-based structure topology optimization is the most popular method. Here is its mathematical description, including the objective function and the constraint condition. Generally, we need to make the discretization, then the problem can be easily solved by finite element method. The design variable is the density. There are two kinds of mathematical models which are very popular. One is called SMP, using continuous density. Then the problem can be solved by highly efficient algorithms. The other is called BESO, using discrete density, which is easier to describe, but its solving algorithm is not so efficient as those of SMP. It is worth mentioning that these two methods both have the local minima problem. There are also plenty of researchers trying to use some intelligence algorithms to solve structure topology optimization. First, for example, the evolutionary algorithm and swarm intelligence reverse the dense sensitivity function to guarantee the efficiency and convergence, and use the intelligent algorithms to enhance the global search ability. The drawback is too many parameters need to turn. Also, there is an unsupervised method named k-means. It's used as an auxiliary to reduce the dimensionality of design variables, but the performance is limited. Some popular machine learning algorithms are also tried, which are linear regression, support vector machine, and shallow neural network. The idea is using them as a surrogate to replace the sensitivity calculation, which is mainly aimed at problems whose sensitivity functions are hard to calculate. Recently, as the deep learning develops rapidly, some researchers try to use convolutional neural network plus generative adversarial network to transfer the original problem to image processing problem. It is said that the computational efficiency can be promoted, but the cost is that plenty of training samples should be prepared, and the different problems need different training samples. What's more, the engineering performance is hard to be granted sometimes. In theory, reinforcement learning can solve all sequential decision problems, like those games from Atari to Go and to StarCraft. The state space and the action space are larger and larger. Combinatorial optimization problems are also included, such as traveling salesman problem and the illegal one knapsack problem. Structural topology optimization can also be viewed as a large-scale combinatorial problem, whose number of design variables is much higher. Referring to the experience from StarCraft, learning from zero is not realistic for these big problems. Prior knowledge is necessary to control the efficiency. Let me introduce a concept named generative design, which means exploring multiple designs under the premise that the engineering performance is satisfied. To achieve it, the formal approaches are changing geometrical dimensions or parameters of problem definition, whose performance is limited. Deep learning is a more powerful method, but the cost is shown as before. Now, we are trying to combine structured topology optimization with reinforcement learning. So our goal is proposing a new framework combining these two fields so as to explore diverse, good but different solutions. Finally, the algorithm is applied to an engineering problem. This section, we will introduce two major methods of density-based structure topology optimization briefly. Here, we use the structure compiling optimization problem as an example. The mathematical description is here. SMP and BSO are corresponding to continuous and discrete variables respectively. A connection between the stiffness and the density is established by controlling the penalty exponent P. Then the elements with intermediate density will be punished. Then the density of elements will converge to 0 or 1. Here is a procedure of SMP and BSO. You can see that they are very similar to each other. The calculation of sensitivity functions and the convergence criterion are the same. The different parts are filter scan, smoothing, especially the update of the density. The two steps with a red star are the parts combined with reinforcement learning. The updating part is very important, which decides the solving efficiency. For SMP, we use optimality criteria, whose performance depends on the choice of the mode limit M. For BSO, its solving algorithm is very similar to greedy algorithm. The evolutionary rate computes the volume fraction needing to reach at the current iteration. In each iteration, all the elements are ranked by their sensitivity, then deleted from low to high. There is another parameter called maximum volume addition ratio in BSO. We don't need to use it in our research. Here is the main part of our study. Exploitation dilemma is a typical problem of reinforcement learning. Means taking unknown actions to gather more information so as to search the global optimal solution. While exploitation means making the best decision based on the current information. There are many four kinds of approaches to balance exploitation and exploration, and we will choose the most representative method among each kind to combine with structure topology optimization to extend the searchability. Those exploration strategies will influence the process of calculating sensitivity or updating elements or both. First, let's talk about naive exploration. Those algorithms all belong to it. The reason why they are called naive is that the exploration is random and can be easily implemented. As a result, they will waste abundant time during the random search. Epsilon greedy is the most representative method, whose idea is mostly choosing the best action at the moment, and sometimes choosing actions randomly. To apply epsilon greedy policy into structure topology optimization, we intend to rank elements according to their sensitivity and divide them into three parts. The lower part is deleted totally, the middle part is deleted randomly, and the higher part will not be deleted. In order to avoid the collapse of the structure, the degree of random research can be controlled by the value of epsilon. In general, epsilon should decrease gradually as the calculation converges. In addition, we propose a concept called search window, which means not only deleting a single element at a time, but also its neighbor elements. The scope can be adjusted by corresponding parameters. Considering some structures with dense meshes, the search window can help enlarge the scope of deletion and enhance the searchability. Optimistic exploration encourages to choose those actions which are hardly to be chosen. Upper confidence bound is a representative method, which has a bonus term on the reward function to encourage exploration. In structured topology optimization, to use UCB, a bonus is added when calculating the sensitivity function. In the bonus term, T means the time of iteration, N means the addition of density in SMP, and N means the time of elements to keep solid in BSO. Thompson sapling is the most representative Bayesian theory and uses posterior probability standard deviation will be chosen. Next, we will use a Bernoulli multi-arm bandit as an example to introduce the procedure of Thompson sapling, assuming that the rewards posterior distribution satisfies beta distribution. First, we sample from beta distribution, get the reward of each arm, namely ZK. Then we choose the arm with the maximum reward. Execute the action in the Bernoulli bandit and get the actual reward of the action. Finally, use the new weight information to update the beta distribution. The procedure repeats in this way. The bottom right figure shows the learning process. Initially, the reward distribution of each arm is all uniform distribution. As the learning process goes by, the result will converge to the action with largest mean and smallest standard deviation. In structured topology optimization, we use the rank of sensitivity function of elements to describe the reward. We try two kinds of distribution, beta and the Gaussian, to fit the reward posterior distribution. The updating schemes are here. The last kind of strategy is based on the information theory. The approach we use here is named information-directed sampling, which is a new research. The action is chosen by calculating the information gain and the expected suboptimality of the action. We prefer to choose the action with smaller expected suboptimality and higher information gain. In structured topology optimization, information-directed sampling mainly works in two steps. First, generate samples and fix the reward function, so as to describe the value of elements. Second, update elements like choosing arms in the multiple arm bandit. It is worth noting that the computational demand is high for this method. Our solution is reducing the number of design variables by dividing those elements into dozens of groups, and the concrete elements are deleted by reverse sampling in each group. The problem of efficiency is solved in this way, but the accuracy is influenced. To get the result we want, we set two metrics to evaluate them. One is the difference of structural compilings with the benchmark to guarantee the engineering performance. The other is intersection over union from a concept in image processing, which is used to measure the difference between structures to guarantee the diversity. We demonstrate our proposed approaches on several cases. The first case is the 2D cantilever beam. We use different exploration strategies, different distributions, and two kinds of topology optimization methods. SMP can be only combined with UCB because the other three exploration strategies are not suitable for continuous variables. As a result, on the right hand, generative design can be achieved just by adjusting one parameter for each approach. We also show the stacked view of each approach here. The part with deeper color represents the key skeleton. Here, we use UCB in BSO as an example to demonstrate the information of the results. We can see that all results satisfy the requirement of engineering performance and diversity. We also show the evolutionary curve of structural compliance here. We can see that the value of the peak and the corresponding iteration vary a lot in different episodes, representing different search directions. Now, let me operate the MATLAB to show the running of the algorithm. The code is available on GitHub. We will use UCB in BSO as an example. First, we set the parameter c equals to 1 and run it for 10 episodes. Finally, we get 4 acceptable designs. Next, we change the parameter c from 1 to 10 and run the algorithm continuously. Now we get 9 acceptable designs. Here are their structures. 9 structures. And let me plot the stacked view. The deep color represents the important part, while the light color means the subordinate part. Here is a L-shaped beam, epsilon greedy, UCB, and Thompson sapling all works well, but IDS always diverges for this case. The reason may be that the structure is fragile on the corner. This is a 3D cantilever beam. We don't use the beta distribution here because it is proving to have the same effect as the Gaussian distribution before. Compared with BSO, we can see that gray elements exist in SIMP, especially when the volume fraction is low. And the IDS also diverges for this case, because this problem is very complex, so IDS can't work well. Here is a summary of those approaches, except that IDS fails to work for complex problems. TS and UCB works well for those cases, and due to the large solution space, the drawback of epsilon greedy is not obvious. As for SIMP and BSO, SIMP is only suitable for UCB, and the gray element is a problem, but its efficiency is higher. What's more, as the examples show, beta and Gaussian distribution have the same performance. The next part, we will apply our proposed algorithms to the non-standard pressure shields, which are practical in engineering. The objective function is still the structure compliance. Here is an atmospheric diving suit. We will use it as an example. We only optimize the upper body and neglect those minor structures like holes and locks for simplicity. The corresponding parameters are shown below. Because the thickness is much lower than the size of the shape. The size of the structure must be large enough to guarantee enough elements to be deleted, which needs huge computation source. To avoid this problem, we transferred it to a variable thickness design problem, which means changing the set density of elements on the outer surface instead of removing them. It can be simply achieved by setting p equals to 1 in SIMP. Then the thickness can be represented by density. The goal is optimizing the distribution of thickness without changing the weight, in order to avoid the case that the thickness declines to zero in some region, which may cause the structure failure by leakage or corrosion. We set a minimum density. 4 generative designs are shown here, from above to below. The thickness distribution is more and more uniform, and the stress distributions are more and more similar to the original structure. The sources of error may mainly form using hexahedral elements to fix the curved surface and the simplification in scale. In conclusion, our work seeks to combine density-based structure topology optimization with exploration strategies of reinforcement learning, so as to improve the searchability and achieve the generative design. Then, the validity of our proposed method is proved by several cases and an engineering problem. In the future, we will devote to enlarging the range of application and transfer the algorithm from MATLAB to commercial modeling software so as to perfect the process of geometrical modeling. Third, because the mechanical analysis in each iteration consists of much repetition, we want to optimize it to reduce the redundancy. Finally, reinforcement learning is a fast developing subject. We are looking forward to referring more experience from it to improve the structure topology optimization. Thank you.